Using the general payoff matrix shown here, where any given player can choose option A or B, we assume that player 1 will choose option A with a probability P, and player 2 will choose option A with probability Q. The payoff values are A, B, C, and D, where the payoff to player 1 is just the negative payoff to player B and vice versa. Since this is a zero-sum game, determine the conditions on A, B, C, and D for this game to have a Nash equilibrium, and determine the values of P and Q that give that Nash equilibrium. First, we want to talk about what is a Nash equilibrium, shown here. A Nash equilibrium is a point at which a change in a player's strategy decreases the payoff to that player. So right here, the payoff for player 1 with strategy P is greater than or equal to the payoff to player 1 with a change in strategy shown by T sub I. And then we show the same thing down here. The payoff to player 2 using strategy Q is greater than or equal to the payoff when he switches to strategy T sub 2. A Nash equilibrium can also be seen as a saddle point on the graph of the payoff function. And with this saddle point, we just mean that the determinant, or D, is negative. To start off, to find values of P and Q, we're going to want to use optimization on the payoff function. And well, first we have to set up the payoff function. The payoff function can be seen as the payoff value multiplied by the probability that any given player will choose this square, this being AA, AB, and so on. So going through that, we can find that the payoff function is A times P times Q, B times P times quantity 1 minus Q, and so on, shown right here. Simplifying this, we get this this expression, quantity A minus B minus C plus D times PQ plus quantity B minus D times P plus quantity C minus D times Q plus D. To find P and Q, just like I said, we want to use optimization, so we take these partials and set them to 0. With our partial with respect to P, we find it in terms of Q, so solving for Q, we get Q equals D minus B over A minus B minus C plus D. Same thing down here, taking the partial with respect to Q, we find we still have a P in here. Solving for that, we get P equals D minus C over A minus B minus C plus D. Now, to determine conditions on A, B, C, and D, we want to look at our D equation. Our D equation is given by the second order partial differentials multiplied minus the partial with respect to Q, then respect to P quantity squared. Taking these second order partials, we find that they're both 0. So for D to be negative, we need A minus B minus C plus D to be greater than 0, the absolute value to be greater than 0. And we can also say that A plus D cannot equal B plus C.
All right, so for part B of question 1, we have 2 scenarios. One where the payoff values are 6, 2, 5, and 8, and the other where the payoff values are 5, 3, 2, and 1. So starting with the first example, we plug our values into the equations for Q and P, which plugging in the values for the equation for Q yields us 6/7 as a probability player 2 would choose option A, and we plug it in for the P equation, and that gives us 3/7, which is the probability player 1 would choose option A. So now that we have our values, we simply just go ahead and plug them into the value for M1 of P and Q, and that yields us 38/7. And as this is a zero-sum game, the payoff for player 2 is going to have to be negative of the payoff for player 1. So that means this is going to be negative 38/7. So for the second example, if we plug in our values into the P and Q equation, that yields us the result of -2 and -1, which neither are possible, and neither are inside our square. So we're going to have to take the partials, which taking the partial with respect to p gives us q plus 2, and taking the partial with respect to q gives us p plus 1. So player 2 is going to want to minimize q in order to minimize player 1's payoff. So that means they're going to want q to be 0. Now player 1, who only has control of p, is going to maximize his payoff, so therefore he's going to want to pick the maximum value for p, which is going to be 1. So plugging in our new values of p equals 1 and q equals 0 to our equations for m payoff for player 1, that yields us the result of 3. It gives us the result of -3 for the payoff for player 2. Alright, to find out if this is truly a Nash equilibrium or not, we have to find out if this point is truly a saddle point. So to do that, we have to take the second derivatives of our m function with respect to q and respect to p. Doing that, the second derivatives both give us that they're equal to 0. So now that we know that information, we're going to have to take the second partial derivative with respect to p and q. And that gives us a minus b minus c plus d. So plugging in the values for example 1 gives us a value of 7, which if we plug it into the equation for d, which is the partial with respect to q times the partial with respect to p minus the second partial, that gives us a value of -49. And as d is less than 0, this means this point is a Nash equilibrium, as it is saddle point. So we do the same thing for the second example, and that gives us a value of 1. So that gives us 0 times 0 minus 1. And as d would be equal to -1, that means d would be less than 0, and thus this is a saddle point and a Nash equilibrium point as well.
As previously discussed, we found the point at which we maximize the payoff in a perfect and rational game with p equaling 3/7 and q equaling 6/7 with a payoff of 38/7. If we were to then, let's say, graph the function, the payoff function, we get this image here, and if we look at this in the perspective of the p direction, p axis, player 1 wants to maximize, so they go up to this point here. Player 2 wants to minimize, going here, and we get this saddle point, which is the Nash equilibrium. In situation 2, as discussed, we got some unrealistic probabilities that were outside the unit square. So in order to keep everything in the first octet, we want player 2 to minimize perfectly, so q equals 0, and we want player 1 to maximize with p equaling 1, and that gives us a point in the first quadrant that is at payoff scale 3, n equals 3.
For question 2, we will be analyzing a part of World War II using game theory, where the Japanese had to reinforce their army in New Guinea in the South Pacific. They had 2 options to sail either north or south with probability q and 1 minus q respectively. And the Q's cancel, so this payoff function isn't dependent on Q at all, meaning that there is no better strategy. Any Q that we choose will always end up with us enduring 2 days of bombing. So there is no better strategy than that given by the Nash equilibrium. In order to prove if these are true Nash equilibria, we have to find the value of D, and for Nash equilibria we need D to be less than 0, which gives a saddle point. Again, D is given by the second order, the product of the second order differentials with respect to P and Q, minus the second order partial with respect to P and Q. For this specific problem, with A and B equal 2, C equals 1, and D equals 3, we get this second order partial with respect to P and Q being 2. Plugging this back into our equation for D yields -4, which gives a value for D less than 0, meaning it is a saddle point.
Alright, so in this example, we're going to have, in a baseball game, we'll have a pitcher who has a probability of Q pitching a curveball, or 1 minus Q, which is a fastball. And then we'll have a batter who's predicting whether or not he's going to be hitting a curve or a fastball. Within the box here, we only give, only given is the batting average within the set of probabilities, and the negative of that would be the payoff for the pitcher. With the safe space, we just have that down. And just like we've done before with calculating the, as done before, we're going to be calculating the P and Q values, and by doing that, we're going to take partial derivatives with respect to P and Q, and we get Q equaling 3/5 and P equaling 1/5. Then we plug that into our outcome payoff equation, and we get a payoff of 0.26, and that would be the batter's payoff, which is his batting average, and then -0.26 would be the payoff for the pitcher in this situation. Alright, so now we need to prove that this point is a saddle point. So again, with our partial derivatives equal to 0, and then our partial derivative with respect to Q and P equaling 0.125, we then plug it into our D equation here. This number squared is negative, D is less than 0, therefore it's saddle point.
So here we have a game of Wyatt's creation, where each player gets a red and a black card. Now, the probability P and the probability Q are the probabilities a player will choose the red card. And then there's also probability that someone will choose the black card. So in this game, if both players play the same colored card, Wyatt gets 2 cards. Or if they play different suits, player 2 will get 1 card. This is because this is Wyatt's game and it has to be rigged in his favor. So plugging in our payoff values into the equation for Q and P, we get both the probabilities are equal to 1/2. So plugging in these values into the payoff equation for player 1, which Joe derived in problem 1, we get that the payoff for player 1, Wyatt, will be 1/2, and the payoff for player 2 will be -1/2. And these values represents the amount of cards gained or lost. So second order partials are both going to be 0, and the partial with respect to P and Q is going to give us 6. So we plug those values into our equation for D, and that gives us -36. So as D is less than 0, that means this is a saddle point and a Nash equilibrium point.
Alright, 3, 2, 1. Fuck. That's right, let go. That's right, 2 cards. Alright, 3, 2, 1. Yes,
God.
sir. Yes, sir. 3, 2, 1.
God.
3,
this shit.